Have you ever wondered why helium, despite being so light, floats away so easily, while sodium is so reactive yet large in size? The reason lies in something we call atomic size, a fundamental property that affects how atoms bond, react, and behave in chemical processes. By definition, atomic size is the distance between the nucleus of an atom and its outermost electron shell. We often measure atomic size using the atomic radius, which is essentially half the distance between two nuclei of the same element in a bonded state. It's measured in angstroms, where 1 angstrom equals 10 to the power minus 10 meters. Imagine the atom as a tiny solar system, the nucleus at the center, and the outermost electrons whirling around at a distance. That's what we are measuring. Now let's understand what really controls the size of an atom. There are two main factors. First, the number of electron shells. More shells mean the electrons are farther away from the nucleus, so atomic size increases. Second, the nuclear charge. This is the positive charge of the nucleus and it pulls electrons inward. So, if nuclear charge increases but the number of shells stays the same, atomic size decreases. It's really a balance between two forces, expanding shells pushing outward and nuclear pull drawing electrons inward. For example, atoms with more shells but the same nuclear charge are larger, while atoms with the same number of shells but more nuclear charge are smaller. Now let's track what happens to atomic size as we move across a period from left to right. The number of electron shells stays constant. But the nuclear charge increases because more protons are added with each new element. So, electrons are pulled closer to the nucleus, making the atom smaller. Let's take period 2 for example. Lithium has an atomic radius of 1.55 angstroms. Fluorine drops to just 0.64 angstroms. That's more than a 50% reduction. Interestingly, neon, which is a noble gas, has a slightly larger radius than fluorine. Why? Because electron repulsion in its full shell slightly pushes out the radius. But overall, the trend holds true. Atomic size decreases across a period. Now, what about down a group? As we move downward in a group, each new element adds a new electron shell, pushing the outermost electrons further away from the nucleus. Even though nuclear charge also increases, the effect of adding shells is much stronger, so the atomic size increases down the group. Let's look at group 1, lithium 1.55 angstroms, sodium 1.91, potassium 2.35, cesium 2.67. You can clearly see a smooth increase in size. This is why heavier alkali metals are more reactive. Their outermost electron is farther away and more easily lost. Let's compare atomic trends across a period and down a group. Across a period, the number of electron shells stays the same, but the nuclear charge increases, pulling electrons in more tightly. This causes the atomic size to decrease from left to right. Down a group, additional shells are added with each element. Even though the nuclear charge also increases, the effect of added shells is stronger, so the atomic size increases. This shows that the shell effect dominates over the increasing nuclear attraction when we move down a group. So overall, atomic size decreases across a period and increases down a group, all due to the balance between nuclear charge and electron shell count. Let's quickly recap what we've discovered about atomic size. It's defined as the distance between the nucleus and the outermost electron shell, measured as atomic radius. Across a period, atomic size decreases due to increased nuclear attraction. Down a group, atomic size increases due to the addition of new shells. These trends are governed by a balance between nuclear charge and shell expansion. And these size variations are not just numbers on a table, they explain why fluorine forms tight, strong bonds, while cesium loses electrons like a hot potato. I hope you now understand how atomic size impacts chemical identity and behavior. In the next class, we'll dive deeper into ionization energy, the energy it takes to snatch away that outermost electron. See you there.